But the three most common ones you'll hear about within the realm of physics are big G, the Newtonian gravitational constant, whatever that may or may not be, seems to be a constant of proportionality. You have H bar, aka Planck's reduced constant. It's the one that you divide by 2 pi because if you're gonna have a cycle or something, that's the one that works with the units. Otherwise, you have a 2 pi factor, which you can still do, but uh, computational reducibility in its essence. If you can simplify it, that tends to be cool. And then C, the speed of light in a vacuum, which we basically defined at 9 significant digits right now. So these units, when we combine them in different exponential powers, multiply and divide, we can get the Planck units as we know it, aka our limits of reality. Note, you do need at least 2 additional constants of nature to complete the set, like we had gone through the other day. You need the electric constant, basically epsilon naught, that little thing right there, which is basically, oh God, what is epsilon? It's basically the permittivity of free space. No, excuse me, it's the permeability of free space. I'm sure I've seen these things like hundreds of thousands of times right in front of me. Nobody would ever get confused about units. But we're gonna dive into that a little bit. Just what the heck is going on, because I'm gonna start to work on a video that we'll see what other folks are doing, but we're gonna work on a unit-based video focusing on a very high level pellucid analysis, aka maximum clarity, not just me coming up here. Here's some symbols. You don't know what they mean. Here's some mathematical signs. And then this gets this. And it's like, bravo. You did a whole bunch of stuff. And some people probably followed along statistically. Yeah. Even if I don't follow, there's probably going to be folks out there that follow it better than I do. But that's just life. C'est la vie. I don't speak French, but. Okay. I probably should have. I am a terrible planner at things. Give me a moment here. We're gonna reconfigure a little thing. I'm actually using the eraser to prop up the laptop because, well, actually erase this. All right. I totally forgot we are gonna do that, but we've got a whiteboard. We might as well use it, right? Just because. Rather than me just, here's a Wolfram Alpha thing, here's a bunch of things I'm clicking through. Unless you know specifically what to look for, you're not really. That's the thing. I control everything in the world, but unless it's resonating with somebody, you're like, what the heck is the point? All right. So we got that. We got a marker. All right. So what do we got? Let me go to the side so we can actually have a point here. All right. So our constructors. Here we go. There the Planck. Oh, my squeaky marker. Planck. Constructors. Construct. That's why I can spell sometimes. Ors. All right. Yeah. There we go. All right. So we got 3. You got our big G. We got H bar, a little thingy over there. And then we got C. All right. So this is gravitational. Constant. Part of this is just for me to just lay this out, just because it's a different form. You can have things up on a spreadsheet. You can be calculating stuff here, there, and everywhere, and like that's cool. But sometimes just laying it out, writing it there, and or somebody makes a comment, and it's like, I did not know that or even think of that. So it's a journey, let's say. Okay, this is the H bar is the elementary unit of action. unit of action. All right. Okay, and then C is speed of light. Speed of light. Let's do slash causality. Causality. Now, some folks may disagree with that, but all right. So I got three things here. These are our 3 prime. Well, 3 is prime. So we've got the Newtonian gravitational constant. All right. So basically, this is your whole. It got you. Got a seat over here. Oh, hopefully, I didn't break a window. All right. So this is basically your whole mass 1, your mass 2. So you get your big G, mass 1, mass 2, divided by R squared. So basically, it's just the whole Newtonian gravitational constant. It's a constant of proportionality between, there's nothing else in the spherical cow example of you've got one thing of mass, you get an identical thing of mass, or whatever other mass. You measure the distance between the 2 radii. Okay. Then you take that radius, you square it, you multiply that mass 1 by your mass 2, you throw in your constant of proportionality there. Boom. Okay. You're going to get the gravitational force between those 2 objects. And to be fair, if you did it in Planck units, you're just going to get the Planck force. Because you're going to have, that's why the Planck units are important. That's kind of like the whole thing about this, because if you did it in units Planck, and you're relating everything to another Planck unit or a limit of a constant of nature, like C, the speed of light, or h bar, the elementary unit of action, you're going to get something else out that's Planck. So basically, if you had the Planck mass, which is the maximum the maximum expression of mass within a given volume. That's the best way I can describe it, because basically if you shove a Planck mass into a Planck volume, you're going to exceed the limit and you kind of get a black hole. Seems to be a limit to something. Why? I don't know. Seems like some may say error prevention. I think it might be more accurate as error. No, did I say error correction? I think it's error prevention. That may have been what I said. All right. So basically, if you were to have Planck mass here for your first mass, you get your second Planck mass in there. Then if you took a Planck for a radius, you need a length. That's the minimum thing of length or distance. That's the Planck length. All right. You plug that in there, you square it, you multiply it by your big G, and you're going to get out a force. That force happens to be the Planck force. Now, the reason I'm saying this is because if you look at, you got the gravitational constant. And again, there's some bonus things right here that we don't have. I'm going to skip ahead for brevity's sake, just because we'll take a look at it in the same parameterization. Okay. So I said you did need 2 additional constants to flush out the other dimensionful quantities. And when I say dimensionful, we should probably clarify what we mean by dimension. A lot of times you'll hear like, we live in a 3+1 dimensional space-time. 3 dimensions of space, 1 dimension of time, whatever the heck that may or may not be. To the average observer like us, it's like, well, usually when I'm like walking, it seems pretty flat. That kind of seems like 2 dimensions, but we seem to be able to like go up and down stairs. So like it appears to be 3-dimensional to observers like us doing all our different stuff and things. But time seems to progress. So that's an interesting thing and seems to have remarkable characteristics. But dimension, and again, perhaps English needs a better word for it. Dimension, very often we think, you got a line, that's 1-dimensional. All right, I realize, oh God, it doesn't show up. You get a line, 1-dimensional. All right, you join it together. So if you had to have a surface, this was laid down there, that's still dimensional. And then if you actually constructed that in 3 dimensions, then you'd have something kind of like a cube. All right. And a lot of the time, you'll have different mathematicians and stuff, and they'll build up, and then you'll have the tesseract, which is basically the cube ends up being one side of the face of the actual tesseract, the 4-dimensional cube. Okay, that's in spatial direct dimensions. Now, these have dimensions as well, because gravity, it's basically going to give you the Newtonian constant of gravitational acceleration. Okay. Well, we'll get into why. This is the dimension of action. And again, there are other interpretations depending on what your particular field you're working in, or what. Long story short is the elementary dimensions will end up lining up. So an elementary dimension is something like a length, a line segment, or a period of time, like a second. Then mass is basically, these are intrinsic properties that may be associated with different entities, maybe like a particle or something. Extrinsic is going to be kind of like the aggregate things, kind of like a single molecule of water. It might have intrinsic properties about being like 18.015 atomic mass units per molecule, because that's basically the associated mass with that. Now, is an individual water molecule wet? Or is that something that seems to an observer like us to be an extrinsic property that emerges once you get to a certain amount of stuff? Okay. I realize that was a detour in several different ways, but this is basically made up like c the speed of light. That's a speed. What is that? It's how far you go given a period of time. So you've got a length, and then divided by the amount of time it took you to go that length. Oh, that's a speed. That's the most brilliant one. So this is made up of length and time. So let's go over here and just do the quick characterization. I'm just going to use the little, this might be confusing. I'll use the SI abbreviation. So this will be meters. I'll just do M. I realize MQ. I realize I used M over there. See, this is why notation gets confusing. This is kg. This is seconds squared. And then this guy over here, this is kilograms. You got a mass squared. And then you got seconds over there, and then speed is just meters divided by seconds. All right. I know it's so messy, but basically these are the dimensional ingredients for the stuff that we're working with right here. Now, that was a very long-winded way of basically getting to the point of, in order to get the rest of the Planck dimensions of reality, we need more than just this. What are the 2 others we need? Well, I might as well not be late anymore. You're going to need epsilon naught. So this is this little squiggly epsilon E-ish character with a 0 on it. This is the electric constant. Constant. Long story short is there are different constants and stuff you can use and everything. Basically, you just need something associated with charge or current, because charge is time times electric current. Okay, so that also means charge is current. No. Current is charge divided by time. So it's your charge divided by a period of time, and that's how you get your current. Okay. Time, current equals charge. So then charge equals, okay, yes. I'm sorry, I'm just doing it in my head. Because this will give you a notion of charge. So basically you can end up deriving the Planck electric charge. Some folks, you can do this, you can do Coulomb's constant. You basically just need some notion of electric charge, because that seems to be another method of quantization of different stuff in reality. The other thing you need is some notion of temperature. So you need Boltzmann's constant, and that's little k sub big B. Boltzmann's constant. Boltzmann constant. This is the conversion between temperature and energy. So basically, if you take the Planck energy, and I forget whether you either multiply it or divide it by Boltzmann's constant, and you're going to get the Planck temperature. And then if you do vice versa, the inverse of whatever that was to the Planck temperature, you're going to get the Planck energy. So it's the method of switching between the units of temperature, which is kind of like, I don't know, like it's just the oscillatory motion of the different stuff within a given volume, okay, or whatever you're looking at. So it's a measure of the aggregate energy of the stuff there. Energy, well, then again, that doesn't just go into the whole, well, what is energy? It's the ability to do work. Is that not a good enough definition for you? The ability to do work? I have the ability to do work. You've got the ability to do some work. What type of work? Well, price and participation may vary. Okay, so long story short is, with these 5 constants, we can now construct all the different Planck limits of reality. And again, the main ones are big G, the Newtonian gravitational constant, h bar, Planck's reduced constant, the elementary unit of action, c, the speed of light in a vacuum, so the limit of speed itself. Those are the primary constructors, and then anything that's going to have any type of electric charge or current, you're going to need epsilon naught. And then if you want something with temperature, you're going to need Boltzmann's constant. So, and part of this is, I learned this from Thad, because he was the first one to point out to me that basically you only need 5 individual units, because also within these 5 constants of nature, you can construct 5 Planck units that actually can create all these 5 right here. So the 5 units that you need are basically just the Planck units themselves. So these are the things, and this is how you get to. So you get the Planck time, small t sub b, get the Planck length, L sub b, get the Planck mass, m sub b, and get the Planck charge, charge q, small q sub b, and then you get the Planck temperature, big T. The Planck temperature is huge, sub b. Okay, so basically from these 5 constants of nature, you can derive those 5 Planck units. Okay. Coincidentally, you can go back and forth. You can use these 5 Planck units to construct these constants of nature, because, well, we can multiply, divide, take an exponent, take a square root, right? So I just found that interesting. That originally laid out you only need these guys, and then you realize once you have those guys, all these guys and the other constants of nature made up by that, then maybe you'll have like some magnitude factor. Like these are the dimensional ingredients. So what do I mean by dimensional ingredients? This is the dimensionful stuff that we measure. What do I mean by a measurement? It's a very good question. People are still arguing about that. My general form for what a measurement is, as far as observation, our detector goes click. Our detector, which if it is a digital one, tends to have some magnitude threshold. It hits, it goes click, because we're only going to have so much precision there. Now you might have an analog one, and that's like, what is it actually saying there? So basically, in my mind, these things that we can measure, or at least do a measurement of something's speed, something's momentum, something's, a lot of times to my understanding within CERN, we're measuring the temperatures via calorimeters and stuff. Why? Because that's the equipment we have that can measure temperature. And if we can get that temperature of all the debris material, we should be able to use Boltzmann's constant to convert from that temperature to the energy and use the best theoretical framework we have to construct what the heck is going on for all those crazy events. Because it's like, but listen, if anybody's ever been in a car accident, hopefully you haven't, you could question what the heck type of thing that was after that accident. Now, imagine if this thing is, what is it? A car is probably like a few meters, maybe 10 meters or something. That's kind of big. Yeah, 5 meters or something. All right. You got a car around five meters or so. Okay. All right. Now take that car and shrink it down to about the charge radius of a proton. It's about 10 to the minus 16 meters. What does that mean? Well, that means it's 16 and it's billion. Okay, it's probably about a million billion times smaller. Okay, so go from an accident reconstruction. Again, hopefully nobody's been in an accident. You need to reconstruct what the heck that vehicle was after a terrible accident. Couple of meters. All right. Now try reconstructing things that are about a million billion times smaller. And you want to do it with high precision. Okay. This is where the statistics and stuff come in, because in order to get that precision, we seem to have some limits on our observation. Why? Well, people are still kind of arguing about that. There seems to be a limit of our knowing what the heck is going on for different stuff's momentum and where it is. Okay. That's another story. Long story short is, if you're going to try to figure out what's going on and reconstruct these things, you're going to need a lot of events. You're going to have like billions and billions and billions of events. And of the billions and billions of events, they can only capture the things that seem to be interesting. That's no small task. Power to the folks. So, I'm sorry. I've been ignoring people the whole time. That's sorry. I got onto a little rant about things. All right. Yes, Poindexter. Stuff and things seem to snap together. What's going on, Ray? Good to see you. We need to catch up at some point. I did promise to do karaoke at some point, and I owe other people appearances. I apologize. All right. Sky Mine's commenting. Hey, what's going on, Sky? Let's see. His comment is, we can't see if there is any structure below the Planck scale, but that doesn't mean there isn't some fine structure. I see what you did there. It depends on which framework you're using. I know at least within the Wolfram framework, the claim is that there is something below the Planck scale, because if we get to a limit, it's like, oh, that's just the end of the line. It's, I don't know, is it just a whole bunch of lines? It's just strings, like string theory. I mean, that's a reported thing. And to be fair, if we did build a super powerful collider the size of the solar system, in theory, we could test it. Now, is that practical at our current day and age? I'm going to let other folks choose. I mean, maybe that is the answer right there. But where are we? According to at least Wolfram physics, the claim is there's going to be atoms of existence. Professor Wolfram refers to them as eames. Those are essentially, the claim is, those are the individual building blocks of reality that everything else is made of. However, that may or may not take place. I did some crazy hack where I looked at their numbers and I'm like, well, Stephen Wolfram assigned me some homework. He's like, take a look at these sections here. Okay, I'm going through those sections. Xerxes, the head of the physics thing, gave you a pro tip at lunch. Do a calculation I had done before. And I'm reading through it. It's like, all right, focus on the flux in the causal graph and everything, or in the different hypergraph structures. I'm like, okay, reading through that. I look over the calculation. It's like, dimensions, flux and hypergraphs, flux. What is this? This number is kind of close to the random. Okay, I can't say random to the logarithmic estimate utilizing what's believed to be the age of the universe. That was how they ended up having like this. They calculate a scalar factor, and then they apply those to Planck units. I just noticed that if you take the dimension of Planck flux, and again, this is a complete hack. I'm fully transparent about this, and literally just divide out the dimensions. At that point, you're insinuating there's a preferred basis of reality. And again, there are problems there, but then again, there might also be interesting answers. And again, I ain't no God nor prophet. I don't know. I wasn't there for the beginning, but I noticed that number seemed to line up with what I was told. So I'm like, let me just divide out the dimensions. Use as a scaling factor, and it reproduced the initial projects within the Wolfram Physics Project within like one order of magnitude. I think the initial physics project estimate was that a minimum quanta or whatever of energy would be about like 10 to the minus 30 electron volts. That estimate, I ended up having like 10 to the minus 29 electron volts or something. And again, it was a hack, but it reproduced the numbers pretty well. But it also has that seems more like an elementary unit type thing rather than that shouldn't appear to be the entire universe. And again, probably wrong, but at least within the Wolfram formulation, it is believed that there are things under the Planck scale, and we're just kind of trying to, I believe the technical term is ansatz. This is your educated guess. You ever heard it's like if Feynman wanted to learn the ansatz or something, it's basically your optimum way of saying we're making a guess. Here's our evidence for this guess, but this is a guess. And hopefully that ansatz, our educated guess, will help you be able to explain more with less. And at that point, whatever, you could say it's numerology, but it's like numerology is numerology until you can explain more with less. And again, there's a lot of pitfalls you can run into because you might, we explain this is beautiful. If all of a sudden you break something else somewhere, now you got to explain that. Now you're adding epicycles and everything. And so your ability to explain more with less can go from great to all of a sudden you run into, well, this isn't how reality actually is. So now you got to go back, reformulate, maybe restate your ansatz or your initial hypothesis. You refine it. You look at reality. Look at reality, what it's telling us. And you go on from there. So I'm sorry, that was a very direct question. That is true, Rick. The speed of light is made of epsilon naught and mu naught too. I'm not gonna lie, that was one of the most satisfying things when it's like, all right, constants of nature. How do all these things work? Blah, blah, blah. I'm going through magnetic constant, electric constant. Wait a second. That looks a little familiar. These are exponential powers of like, I can take the square root of this. Let me do 1 over that. Bada boom, bada bing. I discovered what Maxwell did like 150 years ago. The speed of light is 1 over the square root of epsilon naught times m naught. Or the electric constant times the magnetic constant. You take your square root of that, you invert it, boom, you get the speed of light. I was very satisfied. Now, here's the thing. This is why learning is cool, because all of a sudden it's like, wait, this is what all those other people were talking about. You start to quote unquote grok it, so to speak. You start to get it in your head. It starts to make more sense. So that is very true. So to be fair, with just standard mathematics and stuff, yeah, you could probably cancel out C and just put the magnetic constant over there. And then you would just do 1 over that. Okay. All right. Okay, I don't care if I do this for my submission or not. This is just an important explainer in and of itself, just because every time I look at units and everything, I go back, I'm like, either I made like some major mistake or I remembered something wrong. And then all of a sudden, once it starts getting more clear, I'm like, oh, this does make sense. Okay, yes. R is the difference between the center of their mass. Where did I put my? Oh, should probably use my other stand rather than my mail. I have you to open. Oh God, worst YouTuber ever. I know. Where are we? Oh, I like that. A dimension is a degree of freedom. Yeah, that. Thank you. I I feel like I kind of knew that, but that does sound true because if we can keep track of all the degrees of freedom, because speed is a length divided by a time, a velocity is a length divided by a time, but that length has a particular direction. So it's a length over a time. So you get some sort of speed or rise over run. Might be a more mathematical term from oh God, what was it, grade school or something. All right, we got our X, we got our Y. Sorry, we do it this way. We got our X, we got our Y. You get your rise, you get your run here. You can draw a line. Fantastic. All right. But yeah, if we can account for the degrees of freedom, because if temperature is a measure of the average kinetic stuff and things that are going on, and we got our mass energy equivalents, then if you can account for momentum, momentum is just mass in motion. So basically, it's mass times the length, and then over a period of time. The squeaking is like a chalkboard. Okay, so what is worse? Chalk squeaking or a squeaky marker? I'm sure it can be infuriating to people in similar ways. I feel like chalk. Maybe it's just ingrained in my memory because when I grew up, chalkboards were still very prevalent, and we hadn't swapped over to like the erasable whiteboards as much. It's maybe more just was it misocynia, the things where you don't like hearing certain things. Um, yeah, ear trauma. Thomas, Thomas. I was just thinking of you. I I apologize. I saw Ray pop in here, and I had promised that I would do karaoke with her at some point. I still I need to hang out with you and Sully and or it doesn't need to be at the same time, but I owe you guys because I said I would, and then I was a no show. So I apologize for that. Um, we're just talking about the stuff and things of reality and how you might not know all the magical symbols and stuff here, but all I know is if somebody's played Candy Crush or any mobile game where you have that, like, if you played Pokemon and you understand the type system, okay, like Ghost beats Psychic, this beats this beats this. Probably shouldn't fight a Blastoise with your Charmander. Water tends to beat fire. But basically, it's not exactly like that, but it's just you got stuff, it's representative stuff, and things line up in different ways. So there's some random symbols that a lot of folks don't know. It's like, oh, big G, well, that's good. Yeah, it's a capital letter. Yeah, but it's also within physics, it's the short form for, well, this thing here. It's, what's that? Meters. So you got a volume, it's meters squared. So you got a volume, you got some mass, so you got some stuff there, but it's got seconds. So that volume, rather than just going a distance, it seems to be accelerating. So it's kind of like you're in your car. If you're in a car or a vehicle, you're accelerating on the highway. You're going at one speed for 1 second. The next second of time, you're going a little bit faster. So you are accelerating. So basically, the whole gravitational constant is basically can be interpreted as the effective force. I'm saying that in quotes. The gravitational force between two masses given a particular distance, how it's going to affect each other. Now, once we upgrade to Einstein's general relativity, we go from just saying it's the gravitational force to it is the curvature of space time, whatever that may or may not be. Insert your standard, here's a trampoline. We throw a bowling ball in it. Bowling ball hits it to the center. We throw a tennis ball around the side, loops around, and then they tell us, okay, this isn't exactly what's going on. We show those examples. I love those examples. I've gone to like little physics and technology nights at university, and you see people doing that. The kids love it. I still love it. Now, is that an accurate description of what's going on? No. And people be honest about that. It's kind of like saying like string theory. It's like, oh, you played string on a guitar. It's tuned a note on a banjo or something like that. It's a little oscillation. It's like, all right, as a 0th level approximation, you got some little oscillations between your strings and stuff like that. Okay, that's kind of what we're doing. Now, it's not exact. No, that's not actually what's going on. We're thinking that this strings that have different modes that can wrap around different Calabi-Yau 6-dimensional plus manifolds and stuff like that. So it's the 0th level initial approximation that's not really true, but it gives you you can see at least maybe the outside of the facility. You might not know what's going on, but maybe there's a fancy sign and it's like they're working with, I don't know, high energy physics or something. And again, a lot of stuff like if you're going into a theoretical representation of reality, one of the things we got to be careful with is the map is not necessarily the territory, because that's the thing, differentiating the map. All right, we have a map. It helps guide us through. Okay, like, and again, I'm not a quantum mechanic, but within quantum mechanics, very often you'll hear folks say, we have this beautiful theory that's been evaluated to 14 significant digits within the standard model. That's fantastic. Number one, the only thing that's been evaluated to basically that limit is the anomalous magnetic moment of the electron, whatever that is, because apparently it seems to be can act like a little bar magnet. You go around, eventually it needs to correct its little flip there. And it seems to deviate from what we would expect it to be. Why? Okay, the whole point is if we've got the machine that is quantum mechanics, whatever that may or may not be, it seems to work extremely well. Why? A lot of people generally say, we don't know. It sits in this magic box. We promote things to like commutators. We give them hats. We give stuff daggers and everything. It sounds kind of like a little espionage film at that point. But you've got the stuff, and it seems to work. Why? Nobody seems to know. Now, and again, I'm sure there are some folks like you'll occasionally hear somebody like Stephen Wolfram at some point saying that my friend Dick Feynman was very fond of saying nobody understands quantum mechanics. And then within the past few years, he did make the claim saying something along the lines, I believe I now understand quantum mechanics or something. And it's like, to be fair, it's like that is a generalized statement, but like with many statements, very often the caveat, not all, should be either implied or explicitly stated, because you never know where a good idea is going to come from. So, I don't even know why I went on that rant. All right. Let's see. Saturday. Which Saturday? This Saturday? What is this Saturday? What time? I usually have I got like a meeting at like 3:00. Some folks for like an hour or two, maybe after. Okay. Yes. H bar. Yes. Our friends here. Welcome, Charlie. Good to see you, my friend. We're just diving into the 5 thing. And again, I learned this from Thad. It's just a lot of times you'll hear, because at least initially to my things I heard, it's like there's 26 constants in nature. There's 18 constants in nature. There's 19 constants in nature. Okay, here, three constants in nature. Now, what is the purpose? So the purpose is all the dimensional stuff, or as a Sky of Mine had said, a degree of freedom. Okay, so within science, we're trying to measure and quantify all the different stuff that is happening and the things that it's affecting. I could also restate that as we're trying to figure out the things that are going on and the stuff involved. That's probably, for this discussion, probably more accurate. Why do I say this? Okay. The claim is this is the dimensional stuff, the ingredients, if you would, of reality. Yes, I'm doing my best Vanna White. Yes, our constants here. Because from these 5 constants, you can bring everything together and then get the other constants of nature, or Planck units. And from those Planck units, these guys right here above my head, we're just doing the exact same thing because we can break these down. Because this right here, the gravitational constant, okay, my ADD is kicking in. I apologize. So these constructors, these are the derived units we can get from these 5 thingies right here. We can get the Planck time, so that is the minimum unit of time according to physics as we know it. Get the Planck length, it's the minimum length according to physics as we know it. And now we get the Planck mass. The interesting thing is the Planck mass is the maximal mass expression within a given volume of space. Okay. So that's a limit. You go past that, you create a black hole, and then the density is just going to drop. Why? Because the universe wants to, it seems to be avoiding its own destruction, perhaps. I don't know. That raises all different types of questions. Again, not for the philosophy here. And we get the Planck charge here, and that in and of itself is, I claim, and some folks may disagree, it is a maximum unit expression of charge. Because, coincidentally, if you do the whole fine structure constant thingy, so basically you get the fine structure constant is a whole bunch of stuff. I should probably wait off on that. No, we'll just do it. Alpha is defined as elementary charge of an electron or proton squared over 4 pi h bar c and then epsilon naught. Okay. So this is the fine structure constant. Now, this is a dimensionless number. It's very important. It pops up everywhere. Now, the interesting thing is it is a dimensionless number. So this is a dimensionless number right here. And we get charge squared in the numerator. That means in order to get a dimensionless number, this whole thing down the bottom must also be, guess what? Charge squared. What charge is it? It's the Planck charge. So that means you can computationally reduce the whole dang statement for alpha to your elementary unit of charge over the Planck charge. Throw your little brackets over it. Square the whole thing. Bada boom, bada bing. You get alpha. Wait, what? Wait, what? Notice the interesting thing about that little trick we just did with the fine structure constant. It used these 3 constants: the elementary unit of action, the speed of light, and the electric constant. Why? It's a charge thing, so of course it's going to have that in it. There did not appear to be any gravity within there. Perhaps that is telling us something. And again, you could have a philosophical implication for that. This is just, you combine these ingredients in this way. You make eggs. I'm going to make some eggs after this. What do? I heat up a pan. I'm using temperature to increase the energy on that surface there. I put a little oil, so it's going to transfer that energy. So it's also going to help lubricate the pan so my eggs will not stick. Well, it's going to heat up my eggs. It's going to heat up the eggs on one side, but since the egg is kind of going out in a flattish thing, I'm going to have to flip that, not quite 2-dimensional surface, but if I use a spatula and flip it like a pancake, that's kind of flat to me. But then I need to distribute the heat on the other side. Not too much. You take it off, and then you can eat it. And guess what? You've done some chemical transformations, and hopefully, I'm not eating raw eggs. It, all I know is a lot of things in real life make a lot more sense to me because a lot of the stuff I was learning just working in a warehouse, running around like a crazy person. You learn about what jerk and torque might be because you're trying to avoid dying. People flying around, trying to stack boxes, drop them off the dock. Oh God, I missed that. Oh, it was an adventure. You got paid to work out. You had to work. Yes, yes. Where are we? Oh, Charlie. No, no, wait. We're trying not to hate on it. If you can't tell, given what's going on just in reality and everything at this point, I'm like, well, if reality is going to go into literal ludicrous mode, I'm there, dude. Just be honest about this. It is what it is. But all right, Rick. All right. So where are we right now? We got that. Okay. I stalled on the Planck charge. I was just explaining this. The Planck temperature, basically, that is another limit. So that is the maximum limit of temperature. And I think there's a good physics explained video where he goes into it, where it's basically, all right, you had a particle in a box. All right. It kind of bounces from side to side. All right. Make the box smaller. Make the box smaller. If you got a thing and it just keeps on doing this oscillatory thing, basically, long story short is once you get to like the Planck length and you were to have something like the Planck mass in a box there and it were to be oscillating, the oscillatory motion you can convert over via Boltzmann's constant to energy. So basically, if you're going to try to cram something down, if it's going to hit the Planck temperature, that's effectively going to be the Planck energy. And if you're going to try to cram that into a minimal volume, like a Planck volume, you're by definition going to cause reality to, I don't know, collapse, transform, undergo some change from space, time, and matter in motion as we know it to a black hole. Whatever that may or may not be. Personally, I don't think we should call them black holes because, well, they're not black, they're invisible, and the only, at least if we're going by the Schwarzschild calculation, the only real component in there is mass. You got a mass, and then you'll have your event horizon radius and stuff like that. So would it not be more appropriate to call them mass holes? Full disclosure, I'm a mass hole born and raised. I would absolutely love for that to be the case. I'm open to ideas. Hey, baby, why we gotta call him black? I'm just saying, it's serious. Don't get any. Don't spit up any oatmeal out of your nose or anything. You don't want to get that stuff in there. It'll probably be itchy. Oh, wait, that was Charlie. Golly. I'm not gonna lie. Here's the thing. If you're using AI as a tool, I know it. People have such strong opinions about this one way or another, and I get it and everything. I don't mind those explanations at all because if you're using it as a tool and you're using it as a tool to help join things together, that seems like a useful thing. If you're just trying to have it like do everything for you, and I honestly like if you want to submit a scientific paper and English isn't your first language, but most of the submissions are in English, I mean, that sounds like a no-brainer. Because English is not the easiest language. To be fair, I speak American. What is that? It's not the Queen's English. So I can understand that, but it's a tool. It's like anything else. And the tools have reached levels where that's great, but you also want to check. So I think Professor Sean Carroll, I think he said it best as far as a lot of these AI agential agents being used as tools. And I think the way he had said it was something along the lines of computers are really good at solving well-posed questions. So kind of like that thing with like, you may have heard the whole thing. It's like ChatGPT has a physics result. And it's like, Yes, an eternal high and mall. Yeah, no, it definitely helped find a reduced form for this, but it was something about calculating modes for like a single gluon or something like that. Um, it went through, it used the compute, and it found a much simplified closed form for the answer. Okay. So I went from like, I don't know, like 30 something like components or something. It was able to computationally reduce it because great at pattern matching. If you lay out a well posed question and you're looking for it to find a way to reduce things, and a lot of times, like I'll do an input here and like it will start to rephrase, and I'm like, you know what? I didn't think about it in that way. And it's like, I can rewrite it that way. Now, it might be something that it's obvious. I just may not have personally thought about, or something maybe I saw, maybe I didn't even consider it. But until you actually see it, then you can actually do it. So it's like if it's walking me through, like, help me with doing like a Higgs, like a Lagrangian for like the Higgs or something like that. It's like, all right, you're gonna have to have this, you're gonna have this, boom, 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 boom. Quickly see why people set these constants equal to 1. You want to put the whole dang thing in there. Your little single like sentence of notation, it quickly grows to like a paragraph. That's an analogy that's not 100% accurate. So let's see. That is a good point. If you're using your car as a tool, you might actually get to work on time. Yeah. Well, that's the thing. What's it doing? It's getting you from one place to another. Can you do it another way? Maybe. Maybe we'll be in Futurama soon. We'll have those like vacuum tubes, kind of like in the old grocery stores where they put the money in there and it sucks it up, and you're like, I always thought the coolest thing as a kid. You just see it just get sucked up. What do we got there? All right, so they've got like some negative air pressure going up there. It's sucking along the thing. It's helping seal that along, but there's some form of lubrication so it could actually move and stuff. See, that's science. You can just start to break it down. It makes weird things less weird, and apparently, once you get to the limits of some things, like, oh, that seems even weirder. Whether you're going down to the microscope or you're dealing with something with humans, it's like, can you figure out a human? Good luck with that. I've tried. I don't even understand myself. So how the heck do you solve for human? Reality seems easier, but yeah, bouncing between the agents seems to. I'm not gonna lie. I feel kind of like a dick like this. At one point, I'm like talking to a chat. I'm like, should I just go to Claude? Is Claude better? No, no. Within I think 1 or 2 chats after that, I gave it one more piece of information, and actually, it did the code how I wanted it, or at least correctly enough that I'm like, okay, wow. So, also some of the things I like going to sleep to it, because sometimes I'll do one of those things where it's got like a 3-hour video, but it's just listing out things that we already know. But some of those channels actually spend some time on it, because I've noticed you'll see copies of the similar. I like the Sleepy Scientist, because even when I listen, I'll hear it and it will say something that you'll normally hear, but it will give the actual caveat about why it's not always the case. Other ones don't do that. So I'm listening to things. I'm like, wow, I heard this from a very high end lecture, actually not even all that long ago. So it doesn't work. Like, there was that whole thing. It's like, learn Japanese while you sleep, and you're supposed to listen to it. I like to imagine that would be it, but I just soft spoken things that even if you're already kind of aware of, just once you hit that tone where you're in and out there, then you just kind of sleep is valuable. Yeah, no, you just use it as a tool like anything else. So, all right, where are we right now? All right. Oh God, I forgot. Hold on, let me look up. Should probably actually do the actual derivation. So, let's do this. So just so we can share with the class, we'll show what we're doing real quick. Because I forget the exact dimensions of the electric constant. So we need electric constant. So, all right. So here's basically just how you can get everything. So it's okay. The electric the permittivity of space. So this is, all right, so, oh, that's interesting. So if you notice here, we have time and current. So time times current is charge. So this is going to be units of charge and then time. Okay. Oh, that's interesting. So this is, let me write this out. This is going to be charge squared, time squared. So it's going to be Q squared, second squared, and that's kilograms. Oh, sorry. I need to use coulombs because I'm in SI units. Derp. All right, so big C, coulombs squared, second squared, kilograms in the denominator, and then meters cubed down below. So that's, let me just verify that this is actually what it is. So if I put in Planck units, that should be, all right, so Planck charge squared, Planck time squared over, I'm just copying literally the symbols on the board right there and just putting like Planck of the thing in front of it. So like a unit of mass, Planck mass, and then meters, Planck length, and then it's cubes, so boom. Oh no, I did something wrong. What is this? Linear capacitance density, Planck charge, Planck time. Well, there's a 4 pi difference here. Why is there the 4 pi difference? I get the unit. Mass, length, time. Oh. Wait, because oh. Yeah, divide by 4 pi. 4 pi. All right, so it's a dimensionless number to get us to the electric constant. Okay, one electric constant. Oh. Well, let me double check. Okay, because there are 4 pi factors. So that's, okay, so that gives us, because it's a volume term, we're defining it basically as what it would be for a point, I believe. Okay. See, sometimes you'll get, because like, what is it? H bar is Planck's constant divided by a circle. Okay. Huh. That's interesting. Oh, the Planck time is a time. I just realized the error. This too, I need to divide by. To be fair, if there was an extra 4 pi here, we need to divide the Planck time by 2 pi because it's a cycle of time, right? Right? Let's see. Oh, wow. Because we're squaring it. Or do I need to do it by 4 pi? I'm going in the wrong direction. Nope. Oh, should probably Planck length. Do I need the wavelength? Hold on. Wow. Okay. Okay, so I guess it's just, I'm just assuming it's doing the volume thing there, and then we're just dividing by the volume out. So All right. So long story short is that's what I wrote over there. It's Coulomb squared, seconds squared, because when you get coulombs is a unit of electric charge. When you have electric charge and you multiply it by time, you get current. So you get the two things of current there. Okay, we have the right direction. And then Boltzmann's constant is, hold on, let me put this back over here. Boltzmann constant. All right, so our dimensions are mass, length squared, and then time, temperature. All right, so we got kilograms, area, so meters squared over. And then there was time squared, so acceleration, seconds squared, and then big T. All right, temperature. So if we did our same thing with our Planck units, we got our, let's go back. Planck mass, Planck length. I'm just do this. Planck length, no, mass. Yeah, we'll get there. Mass times Planck length. We're really just filling in the Planck units there. Boom. Divide by Planck time squared, and then Planck temperature. Boom. All right. And then by the magic of multiplication, we get Boltzmann's constant. All right. So basically, that's the same thing with these different things. So just to go over for gravity, we get that script is Planck length cubed divided by Planck mass times Planck time squared. Boom. Oh, look. It's the Newtonian gravitational constant. All right, boom. And then if I can go through here and then bar. So Planck. I remember this one. Planck mass, Planck length squared over Planck time. So it'll be 1.105 times 10 to the minus 34 joule seconds. Boom. All right. Produce Planck's constant. Yep. Okay. And then speed is Planck length divided by the Planck time. Minimum unit of length divided by the minimum unit of time gives you the maximum speed of light. What else do we have? Okay, and that was it. Those are the constants and how you can go back and forth between them. Bada boom, bada bing. Cool. All right. Very nice. Oh God, Neuralink. God help us all. Just put my side. I already was in the World of Warcraft matrix long enough. So, but yeah, this is basically the primary constructors of reality, or some may say the dimensional degrees of freedom that we have here. Basically, as far as the dimensional ingredients, the stuff that makes up our reality, that's it. Or this is a particular parameterization that you can reduce it down to 5. These 5 constants. Big G, Newtonian gravitational constant. H bar, the elementary unit of action. C, the speed of light. Epsilon naught, the electric constant. And K sub B, Boltzmann's constant. All right. These 5 constants, we can make all our Planck units. And inversely, from our Planck units, the Planck time, the Planck length, the Planck mass, the Planck charge, and the Planck temperature, we can construct all these other constants of nature as far as the dimensional stuff involved. And then the things, whether you want to divide out a circle, you want to multiply it by a sphere, divide by a sphere, or you apply some type of mathematics to this stuff, those are the things that are going on. Or at least that would be a method of determining all the things that this stuff can do. At least that's my claim. So that's about all I got for right now. So hey, thank you guys for all watching. Peace out, everybody. It's a wacky and wild world out there, but it's open for a better tomorrow. Peace out, everybody.